a little broader in some of the things that he looked at, and so I've invited Ralph in particular to jump in when he wants to expand on something. And by all means, if I make a whopper, please correct me. And there we go. So my presentation is actually based on a seminar course that I took as a recent undergraduate, and this was my term presentation that I made. So I want to acknowledge Professor William Harris, one of the world's great scholars on Rome, and thank him for his inspiration. In the history of the human race, there have been a number of critical discoveries and inventions, interactions between humankind and the environment that changed everything. So, for example, we have to talk about humankind's mastery of fire, its discovery of how to enable much larger populations by growing food and domesticating animals. And to this, we must add humanity's discovery of the secrets of metal and metallurgy, mastery of substances that are strong and hard, and yet at the same time can be made completely plastic so they can be fashioned into any shape and any form. These technologies create the possibility for life as we know it today on a planet that sustains a human population of 7.6 billion individuals. So my presentation will be divided into three basic parts with a little introduction. So the first will be, how does this stuff get into the environment in the first place? A little kind of geologically oriented discussion. Then the second part will be mining operations. How do we get it out of the environment? And third, metallurgical operations, which is how do we turn these rocks and ores into actually useful metal. There are basically four primary sources for ancient mining and metallurgy in the classical world. So there are literary and epigraphic sources, and here I'm referring to Plato, Aristotle, Theophrastus, Diodorus Siculus, the geographer Strabo, Pliny, and Vitruvius. Then there are material remains, mining sites, and associated archaeological remains. However, because these places actually were rich in metals, many of them have ongoing mining operations, and that tends to destroy the evidence of the ancient activity. But we have what we have, and it's extremely helpful. Then we have surviving metal objects, and then finally we have new technological methods. So, for example, this is a paper from 1996 about the use of ice cores in Greenland to look at the telltale signs of copper smelting over time. These authors showed that the emissions related to copper smelting began to increase from the baseline a little before 1000 BC and then rapidly accelerate in the period of the late Roman Republic and the early Principate. Paul Craddock, who's a specialist in the history of metallurgy at the British Museum, relates the results reported by the Hong Kong team to enormous demand for metals, especially silver, produced by the introduction of coinage in the mid-first millennium BC. And so these are the results that they show and the correlations that they show. So where did metallurgy in the modern world begin? So here is a paper from the Journal of Archaeological Science that addresses a question that is, quote, restlessly argued, end quote, by prehistoric archaeologists, which was where and when was extractive metallurgy invented? Some scholars have argued for a single source, the ancient Near East, followed by a gradual diffusion across the ancient world. Other scholars have argued for multiple independent inventions.
Your volume, by the way, reduced somehow just a minute ago. I don't know what you did. You corrected something and we don't hear you as well.
Oh, really?
Yeah, okay. It's more than him. Yeah.
Let me go back to this. Let it switch.
Okay, over. Yeah, now it's better.
Is that better now?
Yeah.
I think the cat was chewing on the wire on my headphones.
Oh my goodness, you don't want an electrocuted cat. That wouldn't be good.
No, the cat is not in danger of being electrocuted. It's low voltage, but they are. I have to fortify all my wires or I wouldn't be able to be online at all. As I said, some scholars argue for a single source in the ancient Near East, followed by gradual diffusion, and others have argued for multiple independent inventions at multiple locations. And the authors of this paper write that the arguments have been primarily based on analysis of ancient artifacts. This can be suggestive, but it is far from conclusive. Harder evidence of a specific site would include stone tools, ores, charcoal, fragments of technical ceramics and installations, furnaces, crucibles, tuyères, which are openings through which air is injected into a blast furnace, and slag and other waste products. In this paper, the authors present evidence for copper smelting beginning at approximately 5000 BC at Belovode in eastern Serbia. This site is associated with what's known as the Vinca culture, which the authors conservatively date from 5300 to 4600 BC. Large amounts of copper artifacts have been found here, representing an order of magnitude greater than those found contemporaneously in the Near East. However, until the research conducted by the authors, there was no solid evidence for smelting ores. And now it's different. Excavations that began at the Belovode site in 1993 showed the earliest evidence for extractive metallurgy found in a layer dated to 5000 BC. These include slag pieces solidified from a copper melt. Slag finds then continue in layers until the last use of the site around 4500 BC. Let me get my pointer up here. Is this? Laser pointer. Great. So, droplets of copper were found that were initially thought to be minerals of the type used for malachite beads, part of what is called the Neolithic package. However, when the finds were cut open, they revealed a dark red section consisting of pure metallic copper, which is conclusive proof of smelted metal. The authors conclude that their research documents the earliest sound evidence for copper smelting known so far. This takes the history of copper smelting back to the very end of the 6th millennium BC, and more broadly suggests the existence of different, possibly independent centers of the invention of metallurgy. So that's the introduction now into the presentation itself. So metal is found in two states. One, it's called native metal, which is pure elemental metal, and that's almost exclusively gold. Occasionally, but much less commonly, for silver and copper, and that's because gold does not combine chemically very well with other substances. So Ralph, I don't know if you want to jump in on this, but you had some detail on why that is the case. Okay, and I'll move forward. And then the second form in which metal is found is ore, which are chemical compounds of metal with other elements, particularly oxides, carbonates, and sulfides. And the metals involved include silver, copper, iron, lead, tin, and zinc. These were the metals that were known to the ancient world, ancient Mediterranean world. Now, these mineral deposits, especially those of economic importance from which metals can be profitably extracted, exist in bodies known as veins. So here we have a vein of gold. Here's a vein of sphalerite, which is a chemical compound, zinc ore, and here we have iron ore. When magma ascends from the Earth's interior, the heat and pressure causes the formation of aqueous solutions of minerals. Veins are formed when these aqueous solutions of minerals enter pre-existing cracks and fissures in the rock formations closer to the surface. The metal-bearing minerals in the veins are intermixed with other minerals that are known as gangue. Gangue minerals have no commercial value and must be separated and removed from the metal-bearing minerals, whether it's natural gold or whether it's ore. And one very common gangue material is quartz. So here we see pure native gold in a quartz gangue. The many different types of veins, the simplest kind of it is what's called a direct deposit vein, which is produced when the material from the magma flows into fissures, and that will be based on the type of rock that's involved in it. In firm homogeneous rocks such as granite, fissures tend to be fairly regular and clean cut, comparatively narrow and reasonably straight. Other types of rocks such as slate and schist are easily fractured and splintered. When these rocks are subject to breaking stress, they tend to form zones of narrow and interlacing fissures rather than straight cracks. Another more complex form is what are called, in addition to the direct deposit veins, there are replacement veins. These form when mineral-rich water acts upon the rocks in the walls of the fissure. The result is that the rock walls become partially replaced by the vein minerals. Instead of the sharp distinction seen in direct deposit veins, we see a more gradual transition between the fissure and the vein. So that's how they get there. So how do they now become distributed in the environment in a way that people can see them and start dealing with them? So the first are what are called placer deposits. So as we've seen, veins are formed through geological processes generated in the Earth's interior and are sometimes affected by surface water that leaches down into the vein. Now, the effects of the forces that act on the surface are chiefly wind and water. So placer deposits are so called because the action of running water washes the vein minerals away and place them down some distance from the source vein. The general principle of placer deposits is that freezing and expanding ice, followed by running water, crack and erode the metal-bearing rock. Pebbles and dust are swept away with the water, and when the velocity of the water decreases, the minerals fall to the bottom, heaviest first. Placer deposits of native gold are the easiest and were therefore the first metal minerals to be obtained from the earth. So here's kind of a diagram of it. We have here a vein of gold that has been displaced by tectonic action and is exposed in an outcrop, and then wind and rain start carrying this down, and we get alluvial gold deposits.
Paul,
Yes, Ralph.
One comment. I think this question of whether gold is certainly the easiest of the metals to extract because it exists as gold form and it's identifiable. Historically, it's not entirely clear. Some of the oldest copper smelting deposits may be somewhat older than the earliest gold. It's not entirely clear. I kind of like the theory that, in fact, gold is actually useless. Copper is really useful. It makes good tools. Gold is much too soft to be any use for anything. So until people decided they really liked bling, copper was much more valuable than gold. Anyhow, just a comment. Which so it's not clear whether copper was smelted, which is extremely difficult, was before or after people started mining gold and using it. Thanks.
Thank you. So here's I want to use one example of how something called a gold field might develop. So we were talking how water would be carrying material and ultimately down from these exposed veins, and water would then accumulate and form rivers. And when I was a kid, we studied something in school called earth science. And one of the topics was the life cycle of rivers. And the basic idea is that a young river, a youthful river, runs straight with very few bends and a very V-shaped valley. And over time, as it erodes the edges of the valley, it starts to curve and meander, and the valley, as we see down here in a mature river, becomes flatter. And then ultimately, in old age, the land is very flat, and we have rivers that meander all over the place, and little pieces of them sometimes get entirely cut off as the water channel moves from one place to another. This, by the way, corresponds very closely to the way the rivers exist in southern Mesopotamia. So, assuming now that these rivers are carrying minerals, so whenever there's a curve in the river, it slows down the flow of the water. And when that happens, the heavier things that are being carried along in the water get deposited on the bottom of the river. So here we're looking at a young river with not very much curvature. But as it gets older, we see that it gets curved and the metal deposits start expanding until we get to the old phase, and we have these basically fairly extensive deposits, in this case of alluvial gold. So that's, you know, not to beat a dead horse, but that's the kind of the basic example of placer, and there are many more complex ways that this happens, but they are very complicated. I don't totally understand them myself, and I think that it's time to move on to how people were able to take advantage of these things and start extracting them. So this is a penax, a black figure pot of Corinthian manufacture from 6th century BC, and it shows miners in the process of working. I want at this point just to take a moment to indicate what my major sources are for the presentation. So Paul Craddock is an expert on early metallurgy and is associated with the British Museum, and the author of a chapter on mining and metallurgy to the Oxford Handbook of Engineering and Technology in the Classical World. His work includes critical analyses of the contribution of new scientific tools and their relationship to archaeological problems. His scholarly rigor about what we know versus what we might reasonably infer versus what we suspect provided me with a corrective to what might be considered Healy's less careful presentation of some of this evidence. So Healy is a classicist and an archaeologist, and his book is Mining and Metallurgy in the Greek and Roman World. And it's a source for my discussion of geological processes, and he also provides very clear and detailed sections on mining and metallurgy. And finally, we have Alfred Michael Hurt, primarily concerned with the organizational measures taken by, in particular, the Romans to exploit the mineral worth of the wealth of the empire. He also presents a wealth of archaeological information about Roman sites. So here's a quote from Craddock, and this is a paraphrase of a famous quote that people might be familiar with concerning the steam engine in the Industrial Revolution. And that quote was that science owes more to the steam engine than the steam engine owes to science. And Craddock's point is that the same thing is true of mining, that despite the developments begun by the Greeks in philosophy and secular knowledge, that absolutely failed to produce any useful understanding of geological processes. In contrast, the practical requirements of mining, namely to move large quantities of air, water, and other materials, had a synergistic relationship with the development of science and mechanics. This is a map of some of the major mining sites in the western part of what was the British Empire. And this is a summary of the major sites and the main metals that were exploited there. Iberia was probably the greatest source of mineral wealth through the first millennium BC, certainly in the Western Mediterranean. Initially used as a source of copper during the Bronze Age, the focus moved to silver mining in the first millennium. The Rio Tinto mines, which were first exploited on a large scale by the Carthaginians, became the mainstay of the Roman Empire. The ancient geographer Strabo and Julius Caesar both mentioned British iron, which was exploited under Claudius and Nero. And the De La Couthi mines in Wales were an important source of gold in Roman times. Zinc ore mined at Aachen, Germany, and Lavaux, Belgium, were used to produce brass. On the eastern side, there were even more sites. And the highlights are the Laurion silver mines in Attica, which is to say near the city of Athens, are quite famous. Herodotus informs us that after finding rich new veins of silver ore, Themistocles succeeded in convincing the Athenian Democratic Assembly to forego a distribution of 10 drachmas per citizen, and instead to use the money to build a navy. Without that, we might all be speaking a dialect of Persian right now. The mines in Dacia, which is now basically Romania and Bulgaria, the conquest of which is celebrated on Trajan's column, the memorial by the Emperor Trajan who conquered Dacia, was one of the most advanced productive mining sites in late antiquity. Alluvial gold deposits at the rivers Pactoclus and Hermus near the ancient city of Sardis, which is in Asia Minor, the western area of what is now Turkey, were the source of the fabled wealth of Croesus, the king of Lydia. Gold mines in the eastern desert of Egypt were a major source of gold for the pharaohs and continued to be exploited in classical times. Mining techniques. So we start with the easiest ones, and basically the way all this stuff goes is that you go for the low-hanging fruit first. So the first techniques were the easiest ones, where particularly with gold, you could just see it on the surface of the terrain. And so for placer mining, where we're talking primarily about native gold, there's no requirement for special processing at all except to free the actual gold particles from the gangue, frequently quartz. This is easy because the gold is mechanically mixed with the waste materials instead of being chemically combined as in ore minerals. So basically you can separate it and you can crush it, but you don't have to chemically reduce it. The gold itself has a very high degree of fineness. This is seen in the high quality of the first Greek coins struck in Lydia in the 7th century BC, once again in Asia Minor. Native gold generally contains up to 99% gold and silver and 0 to 1% copper, iron, and other impurities. So one early method of collecting gold was to put the placer material into troughs of water. Perforations on one end filtered out rocks and stones. The water was then channeled to flow over sheepskin, which trapped grains of ore. The sheepskin were then hung out to dry and beaten to collect the gold dust. Now, this is very tempting for scholars to, and people in general, to connect this with the legend of Jason and the Golden Fleece, but Healy considers that highly unlikely. In Turdetania in southern Spain, soil was washed in pits or troughs. Strabo, the geographer, states that in his day, gold washeries were more numerous than actual gold mines. Panning, which I think we're all familiar with from Western movies, is a technique where a pan or other container is filled with mineral-rich, or in this case, gold-rich dirt. And after discarding the larger stones, the pan is held under the water and swirled about, which causes the heavy particles containing gold to sink. The pan is then tipped forward and the lighter material at the surface is poured off, hopefully leaving you with some gold at the end. Once you get past that, we then have to start really doing some serious technology to get beneath the surface. So we're talking about opencast mining. So it's still easier than deep mining because the native metal lies close to or on the surface. This is placer mining and panning. Opencast mining. These are large-scale techniques used after the easily accessible placer and surface deposits are exhausted. Ore deposit covered by earth is called the overburden. That has to be removed. And there's a technique called hushing to remove the overburden. Opencast mining was widely used in Roman mining operations, and opencast mining lends itself to operations of scale. Major engineering works are needed, and large numbers of men can be employed. The first task, which is to remove the overburden, that is the earth and rock covering the ore, and then two techniques are employed, hushing and ground sluicing, which together require a huge hydraulic infrastructure. So, hushing. Hushing is particularly useful in removing large amounts of overburden. The principle is simple. You collect a large amount of water in reservoirs, in tanks that are elevated above the opencast area. Then you dig shafts into the overburden. You dig vertical and then horizontal shafts, horizontal tunnels that are called adits, and they're cut into the side of the hill to meet the vertical shaft. Then you release the water all of a sudden in a huge torrent, which rushes through the shafts and washes away the overburden, frequently taking large chunks of the mountain along with it. And this is a picture of Las Medullas in northwestern Spain, and you can see the result of having huge pieces of this mountain just washed away by massive Roman opencast mines. Here, the overburden was up to 100 meters deep. In the schematic diagram, we see the water stored in the reservoir above the mineral, then the shaft is adits are cut, and then the water is released, and then it the whole hillside collapses, and the landscape is left with these enormous scars that we see. Now, ground sluicing, after the overburden is removed, mineral deposit has been exposed by hushing. Then the ground sluicing technique is used to wash away as much as possible of the gangue material. Water is directed through a step series of troughs. As the water flows from trough to trough, the heavier metal-bearing minerals sink and the lighter gangue materials are washed away. And here is a composite diagram of operations at Les Medullas. So you can see the stepped ground sluicing over here on the lower left. These operations, as you might imagine, required enormous amounts of water. And just for this one place, the Roman engineers built 7 different aqueducts, which were 1 to 2 meters wide, and the longest was 50 kilometers long. They directed water to tanks with a capacity up to 24,000 cubic meters, and overall 34 million liters of water were delivered every day. Here's a diagram of the Delacuthi mines in Wales, and also using hydraulic techniques to remove the overburden. And you can see the tanks over here at the top of the ridge. And they may have been used to mine alluvial deposits similar to Las Medullas, but other writers believe that hushing at Delacuthi was used to remove overburden and to expose primarily vein deposits. Then we get to the third, last, and most difficult and most dangerous type of mining, is what we typically imagine when we think about mining. So compared to Opencast mining, underground mining was much more difficult and much more dangerous. Ore had to be extracted via shafts, galleries, and tunnels. This created technical problems such as drainage and ventilation, as well as the prevention of tunnel collapse. So here we see some examples of this. Miners drove vertical shafts and horizontal tunnels and galleries into the rock. In addition to providing access for the miners, the shafts were also used to remove the ore. So if we look over here, which is a picture of the shaft at Rio Tinto, if you can see, it's not all that clear, but you can see these darker spots over here. These were basically like a ladder or handholds that were cut into the rock, so that they're essentially steps that could be used by the miners, but not interfere with removing the ore through the same shaft. Here's another gallery at Rio Tinto, this is down here, and you notice that it's much wider at the top than it is at the bottom, which was to make room for the shoulders of the miners as they walked into the gallery. And it shows how narrow and confined the working area was. This greatly limited the productivity of underground mining operations. So, light and ventilation. There's evidence that the Romans used oil lamps placed in niches or on ledges, as in the Spanish mines, to provide light. Greek miners used smoky torches. None of this was real good for the miners, and ventilation was a serious problem. Lucretius, Vitruvius, and Pliny all write about miners dying from poisonous fumes. Craddock writes that the movement of air was probably achieved by the use of carefully placed fires at the bottom of shafts in conjunction with doors within the mines. Air would be drawn up one shaft by lighting a fire at its base, and the hot air would rise, and that would pull air through the workings drawn in for another shaft. And so we see here at Cabezas de los Pastos this immense configuration of twin shafts. And there the idea is that one shaft, they would build a fire at the bottom, and that would draw air down from the shaft right next door. And hundreds of these have been discovered here at Cabezas de los Pastos and Sotiel Coronada in southwestern Spain. Light and ventilation. The next problem is drainage. And the Romans were the first ones to really get a handle on this. Prior to the engineering capabilities of the Romans, mines just could not be operated lower than the water table. For example, the Laurion silver mines in Attica essentially stopped at about sea level. The Romans used 3 techniques to provide drainage. For mines on hillsides, crosscuts could be used to drain the workings. So they would go on the hillside, they would drill a horizontal adze, and water could drain out through that. Rio Tinto, for example, had a very elaborate system of underground channels. One channel at Serra del Caveira was more than 1,000 meters long. The Romans also used large numbers of slaves to just simply bail out galleries with buckets. Most brute force imaginable. Copper buckets survived from Cartagena, Rio Tinto, and other locations in Spain. And then we get to the use of mechanical devices. And the first of these is what's known as the Archimedean screw. I think people may be basically familiar with how this works. They're inserted into a receptacle on the lower level, and then as you turn it, the water gets carried up by the screw action until it gets deposited at a higher level. And then you could gang multiple of these things together to gradually move water to a higher level where you could then remove it from the mine. But it's rather, and just to show you that this is a terracotta image from the Ptolemaic period, which shows an Archimedean screw. And here we have something from the 1970s showing a farmer in Egypt using an Archimedean screw together with an irrigation system to move water from one part of the irrigation system to the other. The water wheel was a big improvement because it could move water much higher per device than the Archimedean screw. And here's an example of one from Rio Tinto, but some scholars have asserted and perhaps proven that this is not assembled correctly. Then the tools. The main innovation in mining technology in the first millennium BC was the introduction of iron and steel tools. By the end of the first millennium, what Craddock refers to as the complete pre-modern kit of mining tools was in use. Picks, hammers, wedges, chisels, hoes, and rakes. Roman tools from Rio Tinto have been shown to have been made of heat-treated steel with properties comparable to their modern counterparts. Mine materials removed in baskets or small trays. Then we have to consider the workforce. The men who wielded these tools were an unhappy lot. Conditions were extremely cramped and dangerous. Ore and rubble had to be removed via the same shafts that workers used to enter the mines. Galleries were frequently too low for a man to stand erect and required the miners to lie on their sides to chip away at the ore. They suffered from heat, poor ventilation, and the threat of cave-ins. The labor force seems to have been made up largely of slaves and criminals. Craddock writes that servitude in the mines can be viewed as a form of capital punishment extending over a great period of time. The Latin phrase is damnati in metallum, those who are condemned to the mines. And Roman law defined a special class of slave called the servus poenae meaning slaves of the penalty. Unlike other Roman slaves, the servi poeni could not be set free by their masters. They could not be manumitted, nor could they buy their freedom. It was a lifetime death sentence. You worked till you died. Regarding these unfortunates, Healy references a passage from the 1st century BC Roman poet Statius. In his Thebaid, Statius uses a simile. He's talking about a wrestler who was killed in a match, and he compares it to a miner. And he says, just as when the Iberian miner buries beneath a hill and leaves far behind the living day, then, if the suspended ground has rocked and the tunneled earth crashed down with sudden roar, overwhelmed by the fallen mount he lies within, nor ever does his crushed and utterly broken corpse deliver up the indignant soul to its own skies. In addition to literary evidence, we have physical evidence as well. This picture shows part of a human foot in iron fetters that was found in the Rio Tinto mines. Most likely it belonged to a slave who died in a cave-in, paying with his life for his society's hunger for metal. That's the end of part 2. On to part 3. Let me pause for a moment here. Is any questions, comments on the mining section of the presentation?
Yeah, I have a comment. A couple of people mentioned in notes that native copper was found by North American Indians or indigenous people. And in fact, yeah, there are some copper implements with indigenous copper. People mentioned, I guess, Minnesota, Michigan. It seems to be that area in particular. So they had some copper tools, but North America never developed smelting. And so their copper tools were, and I guess they never developed bronze. So their copper tools were pretty limited. It's not until you get smelting. Native metal, well, gold is native metal. Other native metal like silver and copper do exist, but they're pretty rare. So if you really want a large quantity, a large scale production of metal, you've got to get the ores and smelt them. Thanks.
Okay, and that's a terrific segue into this section.
Oh, I just wanted to add one thing.
Please go ahead.
It was Hallstatt in Austria. It was built into the side of the Dachstein, and it was a mining town. The mine was very close, and they would take the wood to timber the mine and also make the charcoal off the side of the Dachstein, which reciprocated by burying the town at one point.
Interesting.
That's right. Yeah, my smelting. If you want to smelt metal in bulk, it requires an awful lot of heat, and so mining areas are often just denuded of trees because they strip all the trees and have to go further and further away to get the wood to make the charcoal to smelt them at the ore. Thanks.
Okay, so metallurgy began with the collection of native metals, primarily gold, but also silver, copper, and meteoric iron. I had previously said possibly meteoric iron, but Ralph showed me that this is a definite thing. This is proven. And then these materials were worked with simple mechanical techniques, hammering, cutting, and grinding. Then came the discovery that certain rocks, or minerals, could be chemically transformed in the heat of a furnace to produce metals. This led to the development of alloys such as bronze. After a considerable time, control over the smelting process improved, enabling the production of iron and steel. Oops. So metallurgy comprises the processes associated with preparing the ore, which is called beneficiation, the extraction of the metal from the ore, which is smelting. Beneficiation refers to processes that concentrate the ore, which are things like milling, washing, and roasting. Smelting refers to the use of a furnace in which chemical reactions allow workable metal to be extracted from the ore. Iron is a special case. Additional mechanical processes, hammering, tempering, quenching, and annealing are required to obtain workable metallic iron. Milling is pretty simple. Basic ways to crush or grind the ore to a fine consistency that would allow for the easiest extraction of metal in the furnace. Mortars and pestles were used, as well as various types of mills. It seems that the work was considered less strenuous than other tasks, and both Diodorus and Agatharchides comment that it was performed by women and older men. So Diodorus says, thereupon the women and older men received from them a rock of this size and cast it into mills, of which a number stand in a row, and taking their places in groups of 2 and 3 at the spoke or handle of each mill, they grind it until they have worked down the amount given to them to the consistency of flour. And more from Diodorus, they grind or crush the lumps, which holds the gold dust in this case, and after washing it out with water, the earthy elements in it, they give the gold dust over to be melted in the furnaces. Strabo says the silver-bearing ore was crushed and disengaged in water by means of sieves. Then the sediment was again crushed and again strained, through the waters meantime being poured off. The fifth sediment was actually smelted. So this is a reconstruction of what were washeries at the silver mines in Laurion, which is in Attica. These were owned by the polis of Athens. And basically what this involves is an enormous tilted table with a water channel that runs around the side. At the top, there is a water cistern. We can see it. Here's the top view of the same thing, right? So here's the cistern. And then over here, there are jets, which would release the water from the cistern. The ore would be poured into the trough, and then the jets would flush it around the table. And when it would reach the corner, just as we saw when there was a bend in the river, this would cause the water to slow down in velocity, and the heavy materials would be cast into these settling tanks. But nothing is simple in that other scholars say that that this is all wrong, and Craddock cautions that we don't know precisely how it worked, but Healy, who's a little more speculative, ventures this reconstruction. This is from Healy's book. And here are what the archaeological remains look like. This is the water storage cistern at Laurion. And these are the jets, which are basically just a funnel. So the water in the cistern would be released through these funnels, which would turn the water basically into jets, just the same way as when you hold your thumb under a water faucet and it makes a jet of water come out. And then here is the water table partially restored. So that's beneficiation. Then we get to smelting. And that's my final topic, which is the heat and chemical reactions that occur in a furnace that are used to separate useful metal from processed ore. So this slide shows the evolution of the metallurgical furnace. And I show this because there's actually a debate among scholars where some scholars maintain that there was little or no technological development occurring in the classical world.
Paul.
Yeah.
Could I go back to that last one a second? My understanding, and I sort of looked this up as we discussed it the other day. I think this was used to separate. I think the ore here was largely a lead. These were, the goal was to get silver out of it, but silver was combined with lead. There was a lead ore which had a small proportion of silver. And you can wash, lead ore is a bit unusual in allowing for washing, because the lead ore, the galena, is much denser than ordinary rock. Iron ore is a little bit denser, copper ore is a little bit denser than rock, but not much. But lead ore is quite a bit denser. And if you don't get it's not as easy as with gold, where the gold is much denser than rock or water. But you can do, if you're careful, you can do some sorting of the lead galena from the rest of the rock, and then you can smelt the lead galena into lead, and then you can extract silver from the lead. And I think this is what was happening in Greece at Laurion. Thanks.
Thank you. So, pretty clear that there was constant technological development going on, at least in this area of metallurgy. And I think our experience is that this is what human beings do. Human beings make things better. Just in the process of doing anything, they'll say, well, how can I do this more efficiently? How can I get more result for less effort coming in? And it's just what it means to be a human being, is to transform your processes to make them more efficient. So this is a diagram of furnaces that the Romans used in Britain to produce bun-shaped copper ingots. So the ore and the charcoal are ignited in the furnace. And Healy hypothesized that this is done at night in order to make it easier for the operators to see the color of the flame, because this was their only way of gauging the temperature. They had no thermometer, they had no other way except direct observation to know what the temperatures were. So that was his suggestion. They could see it better at night. Air would enter the furnace through openings shown on the bottom right. And this could be done with bellows, or more primitive ones might be just done in a place where there were prevailing winds that were primarily coming in that direction. The opening would be at the level that would be required. You see the way it's there. It's just at the right level so that the slag, which is a waste product, would be able to run off through that opening, leaving basically metallic copper collecting at the bottom of the furnace. So copper has a very high melting point, 1085 degrees Celsius. And the copper could not be permitted to run out of the furnace gradually, because the metal would solidify before it reached the mold. So therefore, what they did is they would put a clay stopper in over here, and when the entire load, the entire batch was ready, they'd pull out the stopper, and the copper would then flow out of the furnace into the mold. And this is an example of what the finished ingot of copper might look like. Now, this is, I'm not going to go too deeply into this. I'm going to show basically two of the chemical reactions that were used to get metallic copper out of ore. And let me say that when I first learned about this, I was really surprised, because I had thought that we all know that charcoal is key to these mining operations. And I had been under the impression that the purpose of the charcoal is just to produce great heat, but that is not true. The purpose of the charcoal is to produce heat, but it's also to be a catalyst for the chemical reaction. So what we see is that two carbon atoms in the charcoal would combine with oxygen to create two molecules of carbon monoxide. And then the carbon monoxide under heat would react with malachite, which is copper carbonate. And then this is a process that's called reduction, where the carbon monoxide would combine to form, carbon monoxide would form two molecules of carbon dioxide, leaving you one molecule or atom of pure metallic copper. That's for malachite copper carbonate. Now, it's kind of similar with copper sulfide, which is called chalcocite or chalcocite. But it's a more complex process. And I wanted to show this one basically to show this. So this is sulfur dioxide. This is poisonous gas. And what this basically illustrates is the deal with the devil, if you will, that we get metal, but we start releasing poison into the atmosphere, making life particularly hazardous for the people operating the furnace, and more generally hazardous for humanity as a whole. So that's pretty good examples of, and then once you get down to this, then once again you have the reaction of the charcoal with oxygen to produce carbon monoxide, and then carbon monoxide combines with copper oxide that was the result of the process over here, right? And then that is reduced to, once again, to metallic copper and carbon dioxide. So chemically, this is pretty simple, and the use of the charcoal really kind of ingenious that it's a double whammy. It provides the heat and it provides the reducing agent to catalyze the chemical reaction. However, smelting iron has special challenges, and the techniques used for iron and other metals will just not work with iron. First of all, the technique of just heating it in the furnace to the melting point and allowing the metal to pool at the bottom of the furnace, it just won't work. And if you were to do this, if you get to that heat and let that happen, the metal that's produced at that point was totally useless in the Mediterranean world. It was that substance is called cast iron, and now we know that cast iron is quite useful, but they were not able to use it in the Mediterranean world. And if this happened and they produced cast iron, it was junk. It was just thrown away. They had no use for it. It was a waste product. And washing techniques to concentrate the ore don't work with iron. Iron needed to be roasted prior to smelting. So this is an example of what the technique that was actually used, something called an iron bloomery. This is done by the Greeks and the Romans. And the bloom, which is produced, is a kind of spongy, rough mass of iron that's obtained from the iron ore. So layers of ore and charcoal were placed in the furnace. Oxygen is injected using a bellows to increase the temperature. And these were first built on windy hillsides to inject the oxygen before the invention of bellows. The temperature would not reach the melting point of iron, so the iron would not become molten and not produce useless cast iron. After 8 to 10 hours, the iron would gradually coagulate into a bloom. The bloom was then removed and reheated in another furnace and then hammered. And this heating and hammering cycle was repeated many times to drive out the remaining slag and the impurities. The result was workable wrought iron. And under the right conditions, this hammering might force enough carbon to alloy with the iron and thus produce steel. This is a shaft furnace that was developed in the 6th century BC and replaced the simple hearth bloomery that we saw above. And this is a depiction of a shaft furnace by the black figure artist Sophilos, who is also the first artist to sign his work. And here's an example of it in action. So the first reference to the iron bloom that we're aware of comes in Homer's.
Paul?
Yes.
Can I make a comment? Just go back one slide. Yeah. You really need to, in order to get hot enough to melt copper, and even more so to reduce the iron, you really need to contain the heat. An open fire, particularly an open wood fire, will only get up to 700 or 800 degrees, which isn't enough to do anything. As you say, for copper, you've got to get up to about 1100. And for iron, well, a little bit more than that, but a similar one. So the only way to do that is to really contain the fire and to blow air on it. You just can't. An open fire won't do it. So and you have to use charcoal, not wood. So charcoal that's contained in a brick or clay or rock, and then you have the shaft furnace, so the air gets carried up, but the heat, you extract as much heat from it as you can through the ore and charcoal mixture as it goes up. So the trick is to contain the heat as much as possible while introducing lots of air. So you get a fast burning fire, but tightly contained. Thanks a lot.
Yeah, so you can see, I'll go back one more slide, and you can see the most primitive form where they just basically layer the materials like that with a clay covering. And then as they get more sophisticated and they have a more efficient process that produces more iron. So, as I was saying, this is, as I said, a black figure pot by Sophilos, and this is another black figure pot by Sophilos, and it depicts a scene in the Iliad, which is the funeral games of Patroclus. And what I'm getting at here is that the Iliad contains what is the first literary reference to an iron bloom that we know of. And in book 23 of the Iliad, Achilles organizes these games in honor of his dead comrade Patroclus, and then he brings out prizes for the athletic competition. And one of them, and then the son of Peleus, that's Achilles, places a mass of unworked iron and says, "Rise up, you who would try for this prize. Even if the winner's fields are very far away, he will have use of this for the turning of 5 years, and not for any lack of iron will his shepherd or his plowman have to venture to the city, for this will supply them." And it's particularly interesting because it shows that even though the Iliad, which is consciously referring back to a past time, some 300 or 400 years before the time of Homer, and in the Iliad there are no iron weapons. All armor and all weapons are made of bronze, though, and there's a mention of even more crudely, helmets that are made from boar's tusks. But bronze is the major metal that's used for armor and for weapons. But the poet kind of slips in a more contemporary reference to show us that iron had become a necessity of life. And rather than talking about weapons, we're talking about very mundane uses of iron. So we have nails, we have an iron beam, and we have the blade of a sickle. And microscopic analysis showed that a higher carbon strip has been hammered onto the cutting edge of the sickle. So I draw your attention to this one verse. Then the son of Peleus placed a mass of unworked iron. And this is my last slide. I wanted to have a little fun. So what I'm doing is contrasting the way major modern translators translated this line from Homer. So we see that Latimer, which is the favored academic translator, and Robert Fagles, which may be the most elegant poetic translation, were not interested to educate themselves about ancient metallurgy. They translated this as pig iron, but pig iron was unknown in Europe until the Middle Ages. Fitzgerald says it was a meteor, but the Greeks had a word for meteor, meteoros, and that word is not in the text. Stephen Mitchell says a cast iron, and as we've seen, that was a waste product in the ancient Mediterranean. It was not useful for anything. And Stanley Lombardo, whose translation is so terse, in this particular case, he basically loses all shade of meaning. And finally, we get to Carolyn Alexander, who did her homework and actually translated what Achilles offered as a prize as what was appropriate to that point in history. I say brava to Carolyn Alexander for doing that homework, and thank you all very much for your attention to this presentation.
Thanks, Paul. Thank you, Paul. This was incredible.
Yeah, thank you. It was very nice.
Excellent. Up questions. I guess the first question I have, Paul, when you were mentioning Themistocles, how would you think that would have worked, where they were trying to give 10 denaries to each person, but ended up building ships to defend themselves against the...
Well, actually, the way it worked is that at that time, it wasn't about the Persians at all. It was about the island city of Aegina, which is a polis up near Argos. And they and the Athenians were warring over the possession of the island of Salamis. And Themistocles was able to convince the Athenians that they needed a fleet to combat the Aegintians. But that was the fleet that they later were able to use to defeat the Persians. And it was just a great sales job. And I imagine that the importance of the island of Salamis, I mean, there's all, this is interesting because of ideology, how ideology comes in to influence these types of political concrete decisions. Salamis was the home of a great Homeric hero, Ajax, the son of Telamon. And I mentioned this in previous presentations. The Athenians did not have a major hero in the Iliad. Then they had a tremendous inferiority complex about them. It was a serious problem for them. And by possessing the island of Salamis, they could claim Ajax as essentially being an Athenian. And this was enough to enable Themistocles to get enough of a popular wave that they were able to walk away from money in their own pocket to build these ships. quite a bit of PR and propaganda and clever use of ideology.
Paul, another question on smelting. Somebody had to come up with this idea that heating this stuff, which can be dug from earth, could produce this nice product, metal and so on. So
Right.
Any idea, I can kind of guess myself that it was after some fire, natural fires, somebody came up with this idea. Any knowledge from archaeology?
Absolutely none.
Distinct
Absolutely none. And I think that your guess is the best guess. There was some sort of accident, and there was some, observant individual or individuals who, and maybe they saw it more than once, and put it together, and because how would you go about trying to do this if you had no idea that it was even possible?
Right.
So it seems to me would have had to have been some sort of accident, in the same way that we have, the reason we know so much about ancient Mesopotamia is because of fires that baked the clay tablets. Accidental fire has helped human beings along the way of technological development.
Right, but then comes the following question. I gleaned from your presentation that smelting was known in very different parts of the world. So my question is, do you think in every place people, or at least in several places, people came up kind of with their own ideas, or knowledge spread from one place to all the others?
I hesitate to venture an opinion. The scholars are yelling at each other about this question, and I'm not really to participate myself in those debates.
Right.
My personal feeling is that it was discovered independently in different places.
Yeah, and maybe some spread too. I mean, both probably good.
Right, but I don't think that you can say that there was one place.
Ralph has some comment, right?
That there was one site of metallurgy, which then spread to every other place.
Yeah, it started with copper, as Paul said. It started with copper about 5,000 BC. Once you can smelt copper, then moving from there to bronze and to iron is just an advancement of the same technique. So it's discovering the smelting of copper that's one theory is that copper ore is fairly distinctive. It's not just a lump of dark metal. Copper comes, malachite is a very rich green stone. So they probably, and I think there's evidence that they were working with malachite or other forms of copper, these green or blue copper semi-precious stones. So they were searching for those and finding those and finding concentrating sites of those. Now, before they started smelting copper, of course, they used fires and even enclosed fires for firing pottery. So they had, it's purely, as Paul says, it's purely speculative. But if you and some pottery, I guess, needs very high temperature firing. So if you developed the furnaces or the ovens for firing pottery, and somehow whether you were experimenting with glazes or something of this sort, or whether you just got a really hot one to
somebody got drunk and dropped piece of
they dropped their bead, right? They had their bead necklace
like that,
right?
But
and it fell into the fire.
Yeah, right. That's right.
Then they went back to try to retrieve it, and they said, "Hey, what's this?"
You know what? I'm sorry. Go ahead, Ralph.
Okay, so they started. So copper was around. One thing when I started looking at this stuff, one thing I read. So copper was about 5,000 BC. The Bronze Age started around 3,000 BC, and then the Iron Age. So the Copper Age, which I thought of as sort of a very short period, lasted for about 2,000 years before
Yeah.
we developed bronze, and then bronze was the primary metal until around
1200 maybe.
around
1200, yeah.
around 1200
Yeah.
that they do that. And and I think it's Paul sort of sketched, when you first make iron, cast iron, not just cast iron, but even the worked iron from the Bloomery iron is no better than bronze. Bronze is pretty good stuff once you've got the precise proportions and you got the tin and the bronze. But with the 1200 Bronze Age collapse, it may have been much harder to get tin.
Right.
Copper is fairly common. Tin is pretty rare. So getting the tin to make bronze was a major challenge. Iron ore is everywhere.
Right.
So when you have a breakdown in your supply of tin, you start using iron. It's not as good as bronze, but then as Paul said, once you start really hammering it and working it and forging it and so on, you can work a little bit of carbon into the surface layer of the wrought iron, and then it becomes primitive steel. And then
Right.
at that point, it starts becoming better than bronze. So if you get back to your supply of tin, you don't really want to go back anymore. You've got something that's even better. But initially, wrought iron was not better than bronze. Thanks.
You know, and if you go to the Metropolitan Museum and you go to the classical galleries, and they have a pretty extensive exhibit of armor, and they have this, particularly they have these helmets, the Corinthian helmets, and they're all bronze. And this is solidly in the Iron Age. You know, these are dated from the 600s BC, but they're still making their helmets out of bronze.
I just wonder, there might be another accident, how they learned to do the bronze, right? After 2,000 years, there must be somebody experimenting. They also, besides tin, I think they used arsenic, right?
Right,
also,
arsenic before tin.
Yeah, it's, you know, but it must be another incident, or somebody tried to add different metal. How did they come up? You know, that's also very interesting. But you know what I wanted to say, what the most puzzling to me is that we found the first in Vinča, right, which is the contemporary Serbia. And this is the territory where there is no major civilization exists, nothing in Mesopotamia or Egypt, but in some Vinča, some settlement of no major civilization. How come they were before, you know, all the major civilizations? Nothing developed as a result of it. You know, they apparently would have a great advantage, but still, isn't that strange?
Well, that's you know, this expression which Melkin gave motto science, or to, in this case, to general culture than otherwise. So,
yeah, but nothing happened to the culture. They didn't develop.
It's not uncommon that we find that people that were, you know, considered culturally backward had advanced metallurgical skills relative to, you know, the classical civilization. So I think the Celts and the Germans, you know, they were advanced in metallurgy, even though the Romans made fun of them because they, you know, they would eat butter on their bread and wipe it on their wagon wheels as grease. And we see that the Indo-Europeans from the steppe, the people who first invented chariots, did it in the context of metallurgical centers in what is now Uzbekistan and southern Russia. And these were people who were, you know, burying horses in mass graves and were kind of the predecessors in many ways of the Vedic religion of India and the primitive Iranian.
But you see, they spread out as a result, and they kind of conquered or dominated a huge territory as a result of this advances.
And they also supplied, in other words, they were the ones who supplied metal to Mesopotamia. Mesopotamia didn't have the materials.
Yeah, but Vinci didn't develop into anything. They had a huge advantage over everybody, even in terms of, let's say, hunting. You know, they should have really had a lot of abilities to produce more food, expand, and certainly in terms of weapons, they would have a huge advantage. And yet nothing came out of it. It's a little puzzling, and they're so much earlier than the other smeltings, right? What's the next after this? Another 1,000 years? Do we have anything close to any other sites close to the time besides Vinci? Anybody know?
I think there was also some copper to the east of Mesopotamia in where is it, the Zagros Mountains, or the mountains of perhaps maybe the Zagros Mountains in Iran. Of course, the problem is you can't do anything in Mesopotamia or in Egypt because they're flat alluvial soil and no trees.
Right.
So you don't
No
get
trees, no charcoal.
So you need mountains to give you the ore. The ore comes in active areas. If you have a sedimentary river valley, there's no ore concentrations there. You might have some placer gold, but you don't get any iron ore or copper ore. So you have to extract those. You have to mine those in mountainous areas, and then you have to have lots of trees nearby to make big fires. And I suppose the idea that you have mountains and forests doesn't really provide a strong basis for a high population density, which will give you a city. The cities developed on the river valleys, the fertile river valleys and the plains.
And by the way, this about 5,000 BC also in a way coincide with the migrations of the Anatolian farmers. So this is the time when the Neolithic revolution reached Europe. The Europe only started to settle down and grow the grains about that period, maybe 5,000-6,000 BC. That's very interesting, because in order to smelt iron, you had to be settled, right?
And then that reminds me of what Ralph was said about the Egypt having gold, but they didn't really have that much. They actually did, and we're gonna do a presentation on Nubia. They actually imported a lot of it from, not imported, but they would say, took a lot of the gold from Nubians. And we know all this Amarna period where that Paul had mentioned, where in the Amarna period, other kings from Mesopotamia would ask Egyptian kings to, pharaohs to give them gold as almost, a given, because Egypt had so much of it. And that's how they paid off, I guess. Or
I thought Egypt's main source of gold were mines in the Sinai.
Nubian gold.
Well, Nubian's in the other direction, right? Nubia's south.
Yeah,
I think they say in the east, they say the eastern mountains of Egypt. So there may have been some from Sinai, but I think the major sources were on the shores of the Red Sea, the Egyptian coast of the Red Sea, down towards Nubia.
Ah, I'll see.
We're gonna do Nubian presentation. I mean, it was their. That's how there was so many rebellions that were happening, in Nubia against.
One of the things that when I was doing this research that was striking, is always striking for me, is the ingenuity of human beings. A lot of these techniques that I showed in my presentation, they're still in use. They're still part of what modern mining technology does. And they got this going, in 2,500 years ago, with no science at all, just practical thinking and determination and ambition and curiosity, and probably profit motive.
Yeah, and medieval time alchemists trying to create gold from things.
Right. Well, they didn't have much practical success, though.
Yeah, no.
Yeah, and warfare too played a role in this. You know, they needed to
Yeah,
get
right.
certain metals.
Right. Yeah.
to-
You get better weapons than your opponents.
Mhm.
That's a huge force multiplier.
But what
Right.
was the term philosophical stone or something? Do you remember?
Philosopher's stone.
Philosopher's stone. Yeah, something like this. There was some supposedly material that helped to create gold out of something.
Right. It was supposed to facilitate transmutation of elements.
Supposedly, that's where gunpowder came from, right? Some Chinese emperor was mandated some chemist to create long-lasting serum, and then gunpowder came about of it. You ever heard of something like that?
I haven't.
No?
I don't know anything about you.
It's Chinese. Some Chinese.
Yeah. Of course, it's Chinese. Yeah,
I
but,
do think it came out of their medical experiments. Yeah. In fact, I think the word for gunpowder in Chinese is fire medicine. So the Chinese, I guess, liked these sort of, and they had a fairly developed pharmacopoeia of all sorts of different types of medicine. And this gunpowder was sort of so volatile, so flammable for danger. It must be powerful stuff. Therefore, it must be good for treating some sort of disease. It must be powerful if you start eating it. So it does seem to have come out of medical experiments in China. At least that's the speculative history.
I hope they weren't.
yeah.
I hope they weren't trying to cure gonorrhea with it or anything. That would have been. Now you're done. It's over. Finished. Wow. Oh, we're gonna do the history of guns and
Gonorrhea.
Well, venereal disease comes from the word Venus. I mean, the name Venus, which is kind of
Right.
so it does,
Aphrodite.
exactly, yes. So it is applicable.
Talking about gonorrhea. On Saturday, we're gonna do Minister of Propaganda, Goebbels. Sorry, and then Sunday we'll have Jewish 11 Wars of Israel. So please do join us. If you have any other questions, we have some latecomers. If you have any questions, throw it by Paul. If not, we could you could just chat in general. Anybody has any? By the way, I'm looking for presenters for Roman history, Romans. Anybody wants to step up? Let me know. It's not going to be now. It's probably in June, July. We have, I think, everybody's set for this couple of months. So anybody wants to grab a topic from the presentation topics, or maybe create your own, I can, put that in. Like Sergio, if you want to talk about the Roman legions, or Marion and Augustus creation.
I'll discuss that, but like I said, like later, like in the summer months, like later.
Yeah, it's gonna be July. Yeah, July.
There is a session for that. I think Roman army, right, Zach? I think we did that. We allocated for that, right?
Right. Well, I'm interested in where the stationary army was created versus the militia or citizen army. Definitely that transition would be interesting to know.
Yeah, no, definitely. Just need some time. But yeah, I'd be happy to put something together.
That's a huge subject to,
Yeah, exactly. That is
going from like
area.
The height of the Roman militia army is like, in the 200s BC, and then the big transition is the Marian reforms.
Yeah, that's the biggest, because from what I remember, during the destruction of Carthage, right, which is 146 BCE, the legion is not really formed yet. They're still kind of, it's a semi-phalanx, semi-legion. It's still kind of, it's in a transitional stage. It's not the legion we know. Like it's
and let me also say that we don't really. My belief is we have really no clue about how the legion actually fought. Polybius talks about this checkerboard formation and stuff, but I've seen a lot of military historians looking at this and saying it's impossible.
But at the time of Polybius, it was not fully formed, the legion yet, because Polybius was exactly that time with the Scipio Aemilianus.
It was definitely formed in
Not the
his
way
time.
we not exactly. I remember, I was looking, but because he went with Scipio Emilianus, right, into that in the Third Punic War, and I remember the way they thought. They had different lines for different status, like they had different.
Well, that's what Polybius said, the Triarii and the.
Yeah, that's right. Yeah, so yeah, that's right.
Principe.
We don't see that in the Legion. The Legion that
We do see that. I mean, but the point is that was the Legion then. I mean, that was the manipular Legion of the Middle Republic.
yes,
And then, and so
but
one
that
of
was
the Marin
transitional
reforms
form.
was to replace the maniple with the cohort, right?
Right.
But so the manipular legion was absolutely a true legion. It was different from the legions of the era of the Caesar and the civil wars, and certainly of the empire. But that was the legion. They used the glaive.
You could call it, but it's really very different from the Legion we know after Marian reform, especially. Very different.
Yeah, very different. Right.
Yeah.
I also want you guys to think about throwing some interesting history about Roman Empire, like Caligula and Cleopatra and Caesar relationship. Stuff that like general public would also be interested in.
Sexy stuff.
Sexy stuff, exactly. I mean, it would be something that people maybe court intrigues.
But that's probably the next year, right?
That would probably be next year. But I mean, we can sprinkle something in from earlier, Romans. Obviously, Caesar, probably this year, right? You have to mention Cleopatra. You can't,
I don't know. I don't know how. Yeah, I know you were planning to do it more often, but I mean, we have enough topics to last us. Just till the end, before Empire, right? Before even Civil War, I think, right? We have, maybe like, what did we plan? I already forgot. Up to Caesar, right?
Right, Augustus, right?
Exactly. Right, and I have a feeling, Greg, that we're going to end up subdividing that as well because
exactly, yeah.
There's so much information, and it's really it's rich.
Absolutely, I would love that. And by the way, maybe Paul, you look into it because we already have it all and see how could it be subdivided or some.
Or it may
parallel.
not even just be subdividing. It may just be
Or
going over like the same time period, but from a different angle.
Yeah. Well, right. See, well, maybe it could make some suggestions. Yeah.
Also,
I'm doing some reading, so I'll see what I can come up with.
Right.
Yeah. You have the schedule, right? You see the whole thing, right?
Sure.
The way I divided this, but yeah, definitely. I mean, I really would like to pay more attention and be more detailed this time around.
Yeah, and also an interesting subject matter that people don't really talk about, like different regions and under Roman, and not even under Cleopatra in Egypt under, you could say, as being Roman protectorate, Armenia under Roman protectorate, things like that. Like people don't really talk about things like that.
We have Alcibiades coming up, don't we?
Oh, I can't get a hold of Alex, so I might end up doing that, or I will probably end up moving that. I don't know. I keep texting him. He said he's going to do it, so then I will see. It's coming up on 21st.
It was on 21st, April 21st.
Oh, so it should be soon.
It should be soon. I hope you work it out with Alex. He hasn't done the presentation yet, right?
Done. I'll do it.
It's a really juicy biography.
Alcibiades. Okay.
Yeah, I mean, he's if anything, he's more interesting than Cleopatra.
Yeah.
Well, he wanted to do the what is it called? He didn't want to do the Alcibiades. He wanted to do the other one, and that's and so maybe we got confusion with that.
What other one?
I'll tell you 1 second. Oh, my brain.
Well, why are you looking for that? I would like to do a presentation on Boudica, the Icenian uprising against the Roman Britain. Yeah. But again, I'll do that later.
Yeah, sure. That's
Well,
like
that's already
sometime
into the empire.
around 70 AD, right? Like
Yeah,
60.
that's exactly, that's like
Yeah.
the height of the empire.
Yeah, something 60 AD or something. Yeah.
You have to do Arminius after. I mean, first you do the Boudica, and then Arminius probably at some point, and then
No, Arminius was before. Arminius was Teutoburg forest. right?
Peterburg Forest, yeah.
Yeah, that's
like
9.
3 AD
That's
or
9
something
AD.
like that?
That's 9 AD.
9
This is
AD.
Boudica is like 60 or something, I think.
you
AD.
could do Arminius, Sergio, and then you could do Boudica after. You know, just stay with like
Yeah,
rebellion.
yeah, definitely.
Get a gold rebellion.
But we haven't even started. We you know, there is so many topics, interesting topics in the Republican period.
Well, he wanted,
I mean, there's so much thing. You know, even around the civil wars, you know, the just Catilina conspiracy, pretty well developed. I think we could go into that. I mean, the whole books are written about it, right? About Catilina conspiracy. That could be a separate subject.
well, on the subject, let me just tell you what Alex wanted to do. He wanted to do Republic by Plato. So I'm gonna reach out to him, you know, see if he can do Alcibiades and Republic maybe next time.
Republic is, I don't know if you could do it in one session. I mean, it's a bit too much.
And it's
Republic is like, you need like maybe 4 sessions. There are so many things there. It's
I don't know, he wanted, you know, he wanted to do it. So I mean, you know, look, we could probably split in a couple, you know, and do it, you know, 2 months in a row. Who knows?
yeah. I mean, at least 2 sessions, maybe 3, 4. They're very different. I mean, the first like 5 books are one thing, and then there's another, like at least 3. I would think 3 sessions. There are so many different things there.
Yeah, I mean, you know, we have a lot of good presentations, and hopefully he will tell
Yeah, I would like to go into a continuation of what I've done.